Hello, my name is Nathan Galliher, and I'm a third-year graduate student at the University of North Carolina. And today I'll be sharing my work on chasing superflares from young stars using the Scope. So before I get into what a superflare is, I want to briefly mention just what a flare is. A stellar flare is an intense burst of radiation coming from the release of magnetic energy inside of a star. These events can be low energy, they can be high energy, and they can occur for a wide range of stars, commonly for indoors, for example. The higher energy of these events are called superflares. These are powerful flaring events with energies greater than 10 to the 33 ergs, and they can release enormous amounts of radiation, particularly in the UV end of the spectrum, and they're much less common, much less understood than their lower energy flare counterparts. So why am I interested in superflares? Well, frequent superflares and their associated coronal mass ejections can destroy a nearby orbiting planet's ozone or entirely strip it of its atmosphere altogether. There are several interesting things to learn about these events, but a particular interest to me is the superflare environment around young stars and their impact on young orbiting exoplanets, because these flaring environments might be very similar to that which was experienced by early Earth as life was evolving. So in order to understand this, many current studies compare the effects of flares on field exoplanets to those of early Earth. We're not exactly sure if this is an accurate comparison. So what I want to understand is what flare environments do young planets actually experience, and what is the effect of superflare activity on these young exoplanets? In order to understand this, I need to develop a library of low latency spectral follow-up observations of these superflaring events. To do this, I use the Everyscope, which is a wide field telescope based in the Southern Hemisphere, EFTI, which is a real-time data reduction pipeline for the Everyscope, and SOAR, which is a follow-up telescope with a spectrograph located in Chile. So the Everyscope is based at CTI in Chile. It's a wide field telescope capable of achieving measurements of the entire sky every 2 minutes using 24 small aperture telescopes on a shared dome, and it achieves an 8,150 square degree field of view. It takes an image of this entire field of view every 2 minutes and achieves a limiting magnitude in the Everyscope bandpass of 16. Now, to utilize the Everyscope, we use the Everyscope Fast Transient Engine. This is a data reduction pipeline, also known as EFTI, and it's the key to low latency spectral follow-up of flares that are detected by the Everyscope. So EFTI monitors images coming in from the entire sky in real time, searching for superflares as they happen. And you can see an example of this on the right of the screen. You see the science frame and the reference frames. It subtracts the two and looks for increases in brightness. This allows us to achieve spectral follow-up of superflares within minutes of them being detected. We get many EFTI triggers in a given night, but I want to quickly show you an example of a young star superflare that we got back in January. So on the left, you see the Everyscope light curve for the night of January 4th. And you'll notice that as you go from the left of the light curve toward the right, this is just a measure of the star's brightness over time. You see a very dramatic increase between about 0.25 and 0.3 on the x-axis. This is the detection of the superflare that EFTI found. So we estimate that in the Everyscope bandpass, this was a roughly 1.5 magnitude flare. And later on, we fit the spectra from the star and found that it was likely an M2 dwarf. So those two facts combined, using information from a paper published by my colleague Ward Howard in 2019, gives us an estimate that this superflare was roughly 10 to the 34 ergs in energy. So we also took a quick look at the test light curve and found that it showed very rapid rotation with a period of less than about 0.93 days. And this hints that this star is likely young, probably less than 700 mega years. So we performed low latency spectral follow-up of this superflare detection using the Sorghum spectrograph for about 1 hour during and after the flare. And I'll show you that time series here. I want you to notice that on the left, toward the UV end of the spectrum, there's an increased flux during the early observations. This is because the flare is putting off lots of radiation in the UV end of the spectrum. And you'll also notice that the emission line amplitudes are also increased. And as the flare evolves, this emission line amplitudes decrease. As we'd expect, the star heads back towards its quiescent state. Now, unfortunately, I was impacted greatly. The survey was impacted greatly by COVID. I was hoping to have a library built of these to better understand their evolution and their impacts, but we missed a lot of observing time. But keep a lookout in the future for work done on this project from me and from the Everyscope group. And with that, I'm going to throw up my takeaways and thank everyone for their attention during my talk.